Good morning. Today we are going to discuss context-free grammars where V is equal to VTPS. This is simply a grammar, and here V is the set of variables, T is the set of terminals, P is the set of productions, and S is the start symbol. So as you know, here we have a Chomsky hierarchy. That is, this is type 0, type 3, type 2, type 1. This is type 1 and type this is type 0, this is type 1, this is type 2, and this is type 3. This is type 0, type 1, type 2 and type 3, and these are this is the Chomsky hierarchy, and according to Chomsky hierarchy, this is unrestricted grammar. Type 0 is unrestricted, type 1 is context sensitive, this is context free, and finally this is regular. And for a regular grammar, the production are the form A derives AB or AB or BA or A. That means here every production, that means for all these grammars, the difference lies only in the case of productions. All others are same, productions are different, and if every production is also form A derives AB, BA or A, that means a terminal followed by a non-terminal, a non-terminal followed by a terminal, or a single terminal on the right hand side, and on the left hand side if you have a single non-terminal, that means all these productions are regular. That means this is said to be a regular grammar. And if you have a regular grammar, then you can easily draw the transition diagram for a finite state automaton, and a regular grammar is accepted by, or a regular language is accepted by a finite state automaton. Now we discuss push down automaton. Certain languages cannot be accepted by a finite state automaton, so we are going for push down automaton. See here, this is regular grammar, and this regular using some languages like say L is equal to A power n B power n, A power n B power n where n greater than or equal to 1. These set of languages cannot be accepted by a finite state automaton. That we have already proved using pumping lemma. Using pumping lemma, we proved that A raised to n B raised to n where n greater than or equal to 1 is not regular. So we have to find out another way for expressing, or another way to accept those set of languages. So we are going for another automaton, or another automaton which is push down automaton, and here I am going to have say a new language which is called context free language, context free grammar. Why? Certain languages like this cannot be represented by a regular grammar. So we are going to have a more powerful grammar which is called context free grammar. Here that means here the condition, if a grammar is said to be context free, if every production of the form A derives alpha, that means a single non-terminal on the left hand side derives a set of terminals, non-terminals, and a set of terminals and non-terminals. A set of terminals, non-terminals, or a set of terminals and non-terminals. Okay, that means A derives alpha. Here, left hand side is having a single non-terminal, and on the right hand side you have set of terminals, non-terminals, or a set of terminals and non-terminals. Okay, so this is called a context free grammar. Left hand side is a single non-terminal, right side is having either terminals, non-terminals, or a set of terminals and non-terminals. And see, I am going to have a grammar for this. S L derives a raised to n b raised to n where n greater than or equal to 1. That means I am going to have S derives ab or S derives a s b. That means this is the grammar for generating this a power n b power n where n greater than n. I'll show you how. Suppose that you have to generate a b b b. That means this is a valid grammar according to this. That means this is actually a power 3 b power 3. This is a b b b. Now I'm going to generate this from the start symbol. You are going to generate a s b. That means here this a and this b you have generated a s b. Now we are going to expand and we are going to generate this a and this b. That is a s b b. Okay. Now we have generated this a and this b. Again you are going to generate this a b now. Now you have another production s derives a b. Now you are going to have a. This is replaced with a b b b. That means this is the final string and that we have generated from the start symbol. That means from the start symbol you have generated the string. Now I am going to have the positive for this. From the start symbol we have generated a s b, right? From the start symbol you are generating a s b. Now from the that means this a and b are terminals now, and from this s we are going to generate another a s b. That is, now from this you are going to generate a b. That means this is a b. Okay. Now when you are traversing this like this, this is a b b b. That is the final string. That's the final a b b b. That is the final string. Okay. See, another example I will show you. That is for generating palindrome. Palindrome is a string which is reading the same left to right or right to left. For example, Malayalam. You are reading MALAYALAM, and from this to this side to this you have MALAYALAM. Okay. Now suppose that your input alphabet or input string contains only zeros and ones. That means it's a binary string. I am going to have a context free grammar for accepting palindromes. I am going to have s derives 0 s0 or s derives 1 s1, s derives 0, s derives 1. That is s derives 0 s0, s derives 1 s1, s derives 0, s derives 1. Suppose that I am going to have a string 0 1 0 0 1 1. See, I am going to check whether this is a palindrome and using this grammar. So I am trying to generate the string using this grammar. That means starting with s derives. That means initially I am going to generate this one and this one. So I am going to use this. That is 1 as 1. 1 s 1. See, from this one, this s I am going to generate 0 and 0. Okay. Now 1 0 s 0 1. Okay. Now from this s you are going to generate this one and this one. Okay. That is 1 0. This s you are going to generate 1 s 1 and 0 1. Now from this s, so I am going to have another production also, s derives epsilon. Now from this s you have to generate 0 and 0. That means 1, 0, 1. This yes, I am going to generate 0, yes, 0 and 1, 0, 1. 1, 0, 1. Okay. Now from this you are going to replace this s with epsilon, then that becomes 1, 0, 1, 0. This s is replaced with nothing, that means 0, 1, 0, 1. That means 1, 0, 1, 0, 0, 1, 0, 1. 1, 0, 1, 0, 0, 1, 0, 1. So I have generated a derivation for this. From the start symbol, you are able to reach the final output or final string. And the equivalent tree you can generate. That means this is the past tree or this is the tree you are going to generate. Derivation tree. This is called the derivation tree. From yes, this is 1, yes, 1. And from this 0, yes, 0. Next is 1 as 1. 1, yes, 1. Next is 0 as 0. 0, yes, 0. And from this yes is epsilon. That means when you are reading like this, what will happen? This is 1, 0, 1, 0, 0, 1, 0, 1. That is the final one. So this is context free grammar. A context free grammar is more powerful compared to the regular grammar. That means every context free grammar is regular. Type 3 is a subset of type 2. That means every regular grammar is context free. But certain languages cannot be accepted by, or we are not able to design regular grammars for languages like A raised to n, A power n, B power n greater than or equal to 1, or the set of palindromes. We are not able to generate finite order for that. So there doesn't exist regular grammar for that. So we are going for a little more powerful grammar which is called a context free grammar. The condition for a grammar to be context free is that every production is of the form A derives alpha. That means the left hand side is having a single non-terminal, and on the right hand side you have a set of terminals, non-terminals, or a set of terminals and non-terminals. Okay. And after that, from the start symbol, if you are able to generate the final string, then that language can be accepted by the context free grammar. That means you have VGPS, and using the set of productions, if from the start symbol, if you are able to read the final string, then that language can be accepted. And if you have a derivation, then you can generate a derivation tree for that. In a context free grammar, you can have two types of derivations: leftmost derivation and rightmost derivation. Leftmost derivation and rightmost derivation. Suppose that you have a grammar like this: E derives E plus T bar T. T derives T star F or F. F derives E within brackets or ID. That means E derives E plus T or T, and E derives T star of or F, and F derives E within brackets or ID. So this is a grammar, and suppose that I am going to generate, say, ID. ID is a terminal string, ID plus ID star ID. If I am going to generate this ID plus ID star ID, here the start symbol is E, and if you are using leftmost derivation, you are going to suppose that I am starting with E. E derives from the start symbol only one production. E derives E plus T. E plus T. Now you are going to replace the leftmost non-terminal at every point of reduction. That means if this is derivation and here on the right hand side you have e plus t. E derives e plus t or t. Now you are going to have e derives e plus t. E plus t. Now the leftmost non-terminal is replaced at each stage. That means here in this right hand side you have a non-terminal here. Here this is also a non-terminal or variable. And now I am going to reduce the leftmost non-terminal. That means I am going to replace this e with id. That means e derives id is not there. So I am going to replace this e with t. That means e derives t. That means t plus t. Okay. Now here in this case the leftmost non-terminal is t and t derives f. And I am going to replace this t with f. That means f plus t and f is replaced with id. So I am going to have id plus t. Okay, id plus t. That means I have replaced the leftmost non-terminal e replaced with t, t replaced with f, and f replaced with id. Now this is a terminal. This is a terminal and this is a non-terminal. Now I am going to replace this t with, here the leftmost non-terminal is this t and I am going to replace that with id plus t derives t star f. T star f. Here in this case also the leftmost non-terminal is t. So I am going to replace this t with f. See, this is id plus, you are going to replace this t with f star f. Okay. Now I am going to replace this f with id. F derives id. That means id plus id star f. Okay. Again, the leftmost non-terminal is f. I am going to replace this f with id. So here I am going to have id plus id star id. That means here from this to this the leftmost non-terminal is, so from the start symbol you have product e derives e plus t. Now you have replaced the leftmost non-terminal with t. Now you have replaced this leftmost non-terminal with f. Now leftmost non-terminal is f and that is replaced with id. In this the leftmost non-terminal is t, that is replaced with t star f. Now here in this case the leftmost non-terminal is t and that is replaced with f. Here in this case the leftmost non-terminal is f, that is replaced with id, and here in this case the leftmost non-terminal is f and that is replaced with id. That is why id plus id star id. That means at every step in the derivation process the leftmost non-terminal is replaced. That is why this is called leftmost derivation. That is why we have leftmost derivation. And I am going to generate a pass tree for this. That means e derives e plus t, and now this e is replaced with t, t is replaced with f, and f replaced with id. That is id. E derives e plus t, e derives t, t derives f, f derives id. Now t is replaced with, what is t? T is replaced with t star f, t star f, and t derives f and f derives id. Okay, now this f is replaced with id. So this is the derivation tree for this. That means e derives e plus t, e derives e plus t. Now this e is replaced with t and this t is replaced with f and that f is replaced with id. And on the right hand side you have t and t derives t star f, t derives t star f and that t is replaced with f and f is replaced with id and this f is replaced with id. So that is why you have id plus id star id. If you are looking at this, like this, id plus id star id. The rightmost derivation for id plus id star id is e derives e plus t. Now the rightmost non-terminal is t. Now this t is I am going to replace. That means it is e plus t derives t star f. T derives t star f. Now the rightmost non-terminal is f. Now I am going to replace that f with id. This will become e plus t star id. And now in this case the rightmost non-terminal is t. Now I am going to replace that with f. It is e derives e plus t is replaced with f star id. And now the rightmost non-terminal is f, that I am going to replace with id. That means e plus id star id. Now I am going to replace this e with t, which is t plus id star id. And now this I am going to replace this t with f, f plus id star id, and f is replaced with id plus id star id. Okay, that is, this is rightmost derivation. So here you can have RMD like that. That means rightmost derivation, and here you can write LMD like that. LMD like that. You can replace, or you can write LMD, and this is RMD. Now I am going to have a path tree for this also. This is not a path tree, this is a derivation tree. And the derivation tree for this is e derives e plus t. E plus t. I am going to replace this t with t star of, that is t star f, and f is replaced with id. Now this t is replaced with f, and that f is replaced with id. E derives t, and t derives f, and f replaced with id. So this is again id plus id star id. See, this is the derivation tree which is taken from the leftmost derivation, and this is the tree, or this is the derivation tree which you have taken from the rightmost derivation. That means look at these two derivation trees. This is the derivation tree which you have derived using leftmost derivation, and this is the one you have derived from using rightmost derivation. If both are same, if both derivation trees we have developed using leftmost derivation as well as the rightmost derivation, if both are same, that grammar is said to be unambiguous. If these two path trees are different, this is not path tree. If these two derivation trees are different, that means for LMD and RMD, if it is generating different derivation trees, that grammar is said to be ambiguous grammar. So how will you check whether a grammar is ambiguous? You have to take a string. You have to generate leftmost derivation, you have to generate rightmost derivation, and using leftmost and rightmost derivations, you have to generate derivation trees. And if the derivation trees are different, that grammar is ambiguous, otherwise it is unambiguous. Okay, thank you.